So in this scenario, it's the true difference in proportion of Black and Hispanic students. Man, I really am not writing well today. In STEM versus non-STEM. Now, I do want to go through today and make sure I'm writing everything out, because it'd be easy for me to just verbalize this, but I want to make sure you have, at least every once in a while, go through and give a good example of what the full thing should look like. We do not know the true difference between this. We do have a statistic. My statistic is going to be p hat sub 1 minus p hat sub 2. P hat, of course, being our sample proportion. So let's figure out our sample proportions. We're going to say that STEM will represent p hat sub 1, and non-STEM is going to be p hat sub 2. So let's go ahead and take the time to actually calculate this. P hat sub 1 is going to be, there were 12 out of a sample size of 300. So this is 12 out of 300. And we can figure out that proportion, which should be 0.04.
Yeah.
All right, good. The next one is 75 out of 500 in this case. So 75 out of 500. And that's, is that 0.15? Yeah. Okay. So even just initially, we can see there's a big difference in these two sample proportions. You might already have an intuition. Is there a statistically significant difference between representation in STEM versus non-STEM? Okay. My initial intuition is yes, it is, but I can't quantify it yet. I need to go through the process to do that. So p hat 1 minus p hat sub 2 will be this 0.04 minus 0.15. It doesn't matter which one we called p hat sub 1, p hat sub 2, but the fact that now we chose STEM for p hat sub 1 means we're going to get a negative number, and that's going to make a difference in how we set up our hypotheses. All right, so let's see. That's negative 0.11. So we've got this set up. And maybe here at the top, this is something that is for your own, well, it's good to show it. We know that n sub 1 is 300. N sub 2 is 500. Our significance level, I'll do this one next, is going to be 0.05. We don't really need anything else. That's about it, okay? So we have all of our inputs for our calculations ready to go. And now the question is, what are the hypotheses here? The null hypothesis is always, remember that there's no change or no difference. So how would we phrase this?
So for the null, you could say there's not a difference.
Right. So there is no difference between them. Since P1 minus P2 is what we're drawing inferences about, the null hypothesis is P1 minus P2 will equal what? 0. And that is, the good thing is that this is always going to be our null hypothesis. Now that's kind of true for the other hypothesis tests we've done, but this is always going to be our null hypothesis for differences. Difference in mean, difference in proportions. We're always assuming there actually is no difference. It's the same population, it's the same distribution, it's the same whatever. So because we set it up a specific way, there is a concern. Let's see how this is phrased. The question is that Black and Hispanic females are underrepresented. So we care about a specific direction. I'll go ahead and tell you it's not equals to. That's always a conservative alternative hypothesis because it gives us a bigger p-value. We just double it at the end. And so it gives us a more rigorous answer. But if we have a very specific direction we are concerned about, then we don't need to do not equals to. We can pick greater than or less than. So less than. Okay.
Why two?
What do you mean? Why? What?
Less than two? I think you missed.
Did I misspoke or was I in the middle of? Did I say two? Yeah, sorry. If I said two, I don't know what I was thinking. Yeah, thinking about twos. I'm thinking about 230 specifically. So now we've got less than 0. 2 does not come into play here. Less than 0. And yeah, it is going to be less than because the way we set it up, we said that P sub 1 is our STEM majors. And so we think that the STEM majors are going to be less than the non-STEM majors. And if that's true, then we should get a negative outcome when we subtract those two. All right, so that's good. That's kind of reinforcing stuff we talked about yesterday. Okay, so that is good. And I don't need to write any more on this. So if you want to do a screenshot of that, your prerogative there. Leave it there for about 5 seconds. Okay, now let me clear this and move us on to the next part of it. Now we want to work through this, and we've got the name of the procedure here. This is going to be a 2-proportion z-test for a difference of proportions. And let me show you different ways you could write that because that's a lot to write. That's also a 2-proportion. You'd probably get away with just prop for proportion, though it's a good idea to write out. 2-proportion z-test for, rather than writing that whole thing out, you could certainly say P1 minus P2. So different ways of saying the same thing. You could describe it. You don't have to come up with the official name. And if you'll notice, I could call this a 2-sample z-test. And my whole point in showing you this is not that you need to pick which one you like best. It's to show you that as long as you're pretty clear that this is a z-test, get that part right. It's not a z-interval. It's not a t-test. It's a z-test. That part you need to get right. And you're making it clear that it's related to proportions. So, and you have 2 samples you're dealing with. So somehow convey that, but you don't need to, try and store names of all these tests in your memory. Just get that across. All right, so let me clear this last line. All right, and this is where it's gonna get a little bit interesting when we look at well, that's gonna come later, but actually, it's about to rear its head. So let me just go through this. First of all, let's look at both samples. We have sample 1, I'll just do P sub 1, P sub 2, and we have our 3 conditions. And this is what I'm hoping I don't need to remind you guys of. This is turning into like second nature. And let me just remind you again why we do these 3 tests. Random means this is going to be an unbiased estimator, and we're going to get reliable representative results. 10% says we can use the simpler calculations, and simpler is of course all relative. They might be complicated, but it gets even more complicated if it doesn't meet the 10% condition. And normal, so that when we're done calculating our test statistic, we can use a normal CDF calculation in order to figure out the probability and the p-value, figure out our p-value from there. So if we didn't have it approximately normal, we could not use the normal CDF calculations at the end. Or in the case of means, our t-CDF. So population 1, is this random?
Yes.
Yes, it is. It luckily even says random. So here is where I'll put random sample. And when I put it in quotes, that means I drew it straight from the prompt. And the next one, is it random? P2, is it random? That is. Yes, it is. Separate random sample. So if they say it's random, we consider it random, we move forward. 10%. Do we know that this is 10% or less of the population?
Yeah. There are a lot of students out there who are.
Yeah, we are talking about a certain university. Now, here's the thing. We don't know the size of this university. Some universities have over 50,000 students. And if we're talking about STEM majors versus non-STEM majors, that's going to be many thousands of students. So here's what all we can say is like, we can assume that 300 is less than 10% of the population. And here's where we would even say the population of STEM students at this university. I'm going to be a little bit lazy. I could say basically the same thing down here, just repeat it all, but here 500. So I am being a little bit lazy, but you get the idea. So we don't just want to put 10% check mark, because that doesn't tell the grader, did they really know what they're doing? Or have they been trained to put 10% check mark? Do they know what that means? So anyways, normal, this is the one we have to be careful with, because what we might want to do, and let me show you what's wrong here. So I want to make sure that it's very clear. If you do this, this is the wrong thing to do. If we just did sample size 1 times p hat sub 1, and then sample size 1 times p hat, 1 minus p hat sub 1. If we did this, that's actually not what we do for this scenario. We need to talk a little bit about why. We are assuming that the null hypothesis, we're assuming that these two proportions are equal to each other. And even though we might look at the outcomes of the sample and decide that they're not, we are starting with the null hypothesis that these two proportions are equal. So what we want to do is we want to have a pooled proportion. So if you remember, well, you don't have to remember, it says here at the prompt, there were 12 out of 300 that were Black or Hispanic females in STEM majors. There were 75 out of 500 who were Black or Hispanic females in non-STEM majors. And what we want to do is pool this. So we want to take the total number of Black and Hispanic females out of the total number of people in both samples. And again, the reason why, if this can make sense to you, is that we're going to come up with what we call p hat sub c. It's a combined or a pooled proportion. So we're going to take the number of successes from the first plus the number of successes from the second and put it over the sample size of the first plus the sample size of the second. Because we're assuming this is all one population. There's no difference between these people. And therefore, the proportion overall should be this pooled proportion. So let me do that math over here. If I do this, I can get that's 87 out of 800. All right, and I definitely don't know this one. So let's figure out what p hat sub c is going to be. So we only do this for hypothesis tests. We didn't have to do this yesterday with the confidence intervals, because with the confidence interval, we're not assuming that there's no difference between them. With a null hypothesis, we are. So I got 0.109. Okay, so now let me just do a little bit of erasing here. Instead of multiplying this by p hat sub 1, I'm going to do p hat sub c. We do the combined. All right, now when I move forward, it's going to be N1, which is 300 times 0.109. And then it's going to be 300 times 0.891. So we can multiply those out, make sure we get at least 10 successes, 10 failures. And of course, we'll do the same thing right here.
Real quick, Mr. Davis,
Sure.
How is this different from what we did yesterday?
The checking conditions really isn't different, except that we are using p hat sub c for this. But what we're doing today is we are going to figure out if this difference is statistically significant. We're not making an inference about what the actual value is, what the true difference is, but we are saying we're not finding an interval. So
Okay, so that's why we're using significant level, not
yes,
not that percent.
yes, and yes,
Not the confidence level.
yeah, we're using significance level. Okay. And yesterday we didn't have hypotheses. I started doing that for a second, and then I forgot what I was doing. So yesterday we didn't have hypotheses, the null and the alternate. Now we do. And we're basically going to say, is this result, our conclusion for this is this result extreme enough that we can decide that this is not the result of random chance, and there really is a difference in the enrollment between these two majors. All right, so anyways, if we just wrap that up here, that's all right, that shouldn't be 300, that should be 500. No. All right, so now we can multiply that times the same thing, 0.109 and 0.891. So I'd want to show the numbers here. Let me just start being a little bit lazy on that. So you can calculate this. I'm running out of space, which is why I'm being a little bit lazy. But you can calculate the number of successes for each of them, just show that they're all greater than 10, which will be the case. Okay. So any questions on the conditions? And I'll tell you this, the combined proportion that we found, p hat sub c, we're going to continue using that everywhere that a proportion is needed, except for, well, we're about to do the test statistic. I'll show you where that's coming into play, but that's going to be a big one. Yeah.
How come we use the like sample size for N2 instead of just like the total sample size?
That's a good question. So we're still saying we have two samples that we drew. We want to make sure each one of them is approximately normal because we're combining them together. And what we're saying is that because the assumption is that there is no difference in the true proportion between these two samples that we took, we're going to use the p hat sub c for the proportion, but the sample size still comes from, we had a sample 300 and 500. Our null is that there's no difference, so they both have about 11% representation. So do we have enough successes and failures at that 11% number?
So you could use either the 300 or 500?
You have to use the 300 for the first sample. So notice, maybe I should draw a line right here. I'm checking both of those. So I'm checking all the conditions for my first sample and all the conditions for my second one.
I only saw the bottom half, not the top.
Oh,
I
okay.
don't know why.
That's okay. So now I've checked all my conditions for both samples, and I can say that these are met. I didn't show the numbers, but they are going to be at least 10. Okay. So I'm going to leave this up maybe for a second if you want to get a screenshot. Okay. And now we can move forward to the heart of this, what we want to kind of just jump straight into, and we have to wait on it. So the general formula right here is given as your test test statistic will equal your stat minus your parameter divided by the standard error. So this has not changed. When we did our one sample z-test, one sample t-test, we still had the same test statistic. But now we're going to be using a specific formula. And this is for proportions. It's going to be a z-test statistic. And now my stat is going to be pretty straightforward. We've got p hat sub 1 minus p hat sub 2. The parameter is p sub 1 minus p sub 2 all over the standard error, and this is where it gets a little bit messy. All right, so when we were doing this yesterday, this is essentially going to be the same formula, but everywhere we had p hat sub 1 and p hat sub 2, it's all going to be p hat sub c. So let me write that in, hopefully not too small. P hat sub c times 1 minus p hat sub c all over n sub 1. Notice it's the first sample size. That's going to be my standard error for the first calculation, for the first sample. And honestly, that's the variance of the first sample. I'm going to add that to the variance of the second one. So that's going to be p hat sub c times 1 minus p hat sub c all over n sub 2. So this formula looks pretty nasty. If everyone's good with that, one thing I wanted to point out is that on your formula sheet, and I hope this is big enough for everyone to see. So if you've got it, it gives you, I'm in the wrong spot, right here. For two proportions, it gives you your standard error that we were using yesterday. And then it says, if you're assuming that p sub 1 equals p sub 2, like we are for a hypothesis test, it gives you this formula. And notice it looks a little different, but all they're doing is using distributive property to pull this p hat sub c minus times 1 minus p hat sub c. They're pulling that out to the front. But if you distribute that back into the numerators, it's the exact same formula that we wrote. So algebraically, are you with me on that? Okay. I just want to show you, this is on the formula sheet. Our version looks a little bit different than what you see here, but it mathematically is the same. Okay. And you can see right there, it gives you the formula for p hat sub c. So that's not something you have to have memorized. That's good to know. But just remember, p hat sub c is your combined proportion. And maybe just a way, when you have this is your fun. Just say, maybe you could even circle this. You could say, for hypothesis tests only. So if that's something that you want to have a note for, that's a good idea. So anyways, now we can start substituting some things in. Okay, now we already calculated p hat sub 1 minus p hat sub 2. This is where we get to work with some fun numbers. So it's going to be negative 0.11 minus, well, this is where we have p sub 1 minus p sub 2. What did we assume p sub 1 minus p sub 2 is? 0. So it's 0, minus 0. And I will tell you this now. Anytime we're dealing with differences, the parameter, whatever we plug in here, is always going to be 0. That is the one thing that gets simpler with this. Pretty much everything else gets more complicated. So it's good to have at least one nice thing in life. All right, so now we can plug in actual numbers for the rest of this. P hat sub c we found was 0.109 times 1 minus, which is 0.891. 1, that's a 0, 109. And n sub 1 is 300 plus, same thing in the numerator, 0.109 times 0.891 all over. Now 500 is your sample size. And this is going to be a fun one to calculate, right? So I would highly recommend do this calculation in the bottom first. And if you need to do it in like 2 or 3 steps, that's fine. Maybe you get the standard error right here first, or the variances of each of those, add them together and then do the square root. If you want to split it into a few steps, that's not a bad idea. But from here, I will let you guys actually calculate what our test statistic is going to be, and I will do the same. All right, so this is, the grunt work of all of this. It is negative 4.833. So what I did in the meantime is I used the prop z-test in the calculator just to make sure that it all checks out. And they came up with a test statistic of negative 4.838. We did a little bit of rounding, but we're only off by 5 thousandths. That's pretty good. All right, and that certainly doesn't throw anything off. Here's our test statistic. I'll write it this way. Z equals negative 4.833. Now, again, this is not a like a format you have to follow and copy down onto a page, but you just want to make sure you have this information very clearly labeled. And so you would want to write test statistics somewhere and show what answer you got, and of course show your work along the way. Now, before we worry about the p-value, let's remember what we just did is we combined this to create, and it was kind of embedded in all the calculations we did, but we were basically comparing this by using this specific formula. We're comparing this to a sampling distribution of differences of proportions. And assuming that there is no difference, that's kind of our null in the middle. So our null right here is that, no, there's no difference. There's 0 difference. And that would be also a 0 for a z-score or a test statistic, right? But we got a negative 4.833. So I probably didn't draw this in the right spot. I'm going to draw this a little further over so I have some room to work with. So, okay. So here's your 0. So here's the first negative standard error away. 1, 2, 3, 4, 5. So right here, this is my test statistic. And we're trying to figure out what's the probability of getting a result that small or smaller. And we already know it's going to be minuscule. But we do want to have a diagram so we can show that. And we can also show that this right here is my p-value. So because we met the normal condition at the beginning, we can just use a normal CDF. And we're going to go from negative infinity as the lower bound up to negative 4.833 at the upper bound. And depending on how you type this in, sometimes if you have a really extreme z-score, it'll even give you 0 as the answer. So, you can, at that point, you can just say less than 0.005 or something. But anyways, at this, it didn't give me a 0, it gave me a number. 6.7 times 10 to the negative 7th. So that's, okay, 6.7, what would that be? 10 millionths? So that'd be 100 thousandths of a percent, something like that.
That's our chances
of getting this result or more extreme if the null hypothesis is true. This is definitely below our significance level. So we will definitely reject this. And whether we had done a 1 or 2-tailed test, we would have got the same thing, right? Statistically significant, that is. Doubling this wouldn't make much of a difference. Okay, so having seen all of that, I will leave it up for a second. All right, and let me move forward. And now we can draw our conclusions. And we can say this. Because the p-value was less than the significance level, and this is where we do our 6.7 times 10 to the negative 7th is less than 0.05, we reject the null hypothesis. Null here I'm trying to write, and it's not my day for writing, but that's okay. So now we want to put this back into context. We can say there is convincing evidence that what? Well, look at this. If I just go back to the prompt, I can just copy this verbatim. That Black and Hispanic females are underrepresented in STEM programs. So as much as possible, try and steal your phrasing from the question itself, because that way you're not going to make a mistake. If you try and come up with your own phrasing for this, then you might say things incorrectly to where you're represented, to where you get it wrong or get some points taken off. So this is not an English test where you're trying to be creative. This is convey the information in the appropriate way. Okay.
That's a wrap.
We did it.
It's crazy how long math problems take now, just like in the higher math classes. This was like a 15-minute problem.
Yeah. Now, in reality, ideally, like once you know what you're doing, this, yeah, we spent a heck of a time because I was going through and explaining all of these steps. When you're doing it, this shouldn't take you more than, 10 minutes is fair.
Yeah.
Now, if this is an FRQ, you want to give yourself about 15 minutes per FRQ. So imagine you could get this done in 15 minutes. I think that's fair to do.
I go through all of like the steps. I just have your head in my voice.
Oh, okay, so if
Leave
you're
his voice in your head.
if you're imagining me explaining every step, yeah, you might run out of time. All right. So I didn't know if anyone had meant to take a picture of that. No, that was a mistake. Whatever. Here we go. This is from those posters. And now we've got the null hypothesis. Notice that we're only dealing with proportions today, but you can see what the null and alternative hypotheses will always be. It's always going to be equal to 0, like you said. And we just have to put greater than, less than, or not equals to it. And keep in mind, depending on what you call P sub 1 and P sub 2, you could do it one way where it's greater than, and someone else could switch what they represent and have to turn it to less than. So that will depend on you as an individual. Of course, not equals is always an option. The test statistic, there you go. You can see that lovely calculation, and you can see difference of means will be similarly fun, and it'll have its own extra thing to consider. There's the p hat sub c. So use these references. Of course, you won't have them on the AP test, but you can use them all day long for this class. So no worries about that. I don't know if I have anything to add to it, but there we go. Here are the conditions again. And notice there's a difference here. I kind of pointed this out yesterday, but just barely. For confidence intervals, we're going to go ahead and use p hat sub 1 and p hat sub 2. For significance tests, when we check our normal condition, use p hat sub c. Okay, so that's a good way of keeping it straight. Now we've got other questions here that we can create a confidence interval, and we can see those are confidence intervals. And now this is going to be a significance test. Okay. Let me see. So here's what I might do for these problems. in the interest of time, I might skip just down to the calculation part. I don't want to minimize the importance of the first bits, but I do maybe think that that's something that we can skip over for now. So let's just create a confidence interval so we can see the difference in the process for creating that versus the hypothesis test. All right. So if I just jump down to the calculations part, I'm going to go ahead and label this is that'll be P sub 1 or P hat sub 1 and P hat sub 2. So P hat sub 1. I haven't even read the context yet. I'm just kind of assuming some things. P hat sub 2, maybe I find out I'm doing things wrong. This will be N sub 1. And this will be N sub 2. Okay, we're looking at political office. Candidates for political office, different level of support among men and women. And one candidate finds out 52% of the men say they will vote for him, only 45. So they're asking for different things here. The first one is a confidence interval for the percent of male voters. In this case, for this one right here, I'm going to skip it. This would be the one sample, one proportion Z interval. So we didn't even need to worry about the female vote here. One proportion Z interval. So that's a little more straightforward with the calculations. I encourage you to give that one a try on your own. Then it asks for a one proportion Z interval for females. So we can get those two different intervals. And basically the benefit of doing that is you can see if the intervals overlap. And maybe we can draw some inferences about what the difference of proportions is going to be. So maybe it'd be worth I'm not going to take the time to do it. I'm being a little lazy. So let's just jump down to the 95% confidence interval for the difference in proportions of males and females. So assuming we created a confidence interval for males and a confidence interval for females, and assuming there was an overlap, what do you think that would indicate about our difference? So conceptually, keep in mind that when we do a one sample or one proportion Z interval, we're saying that any of these outcomes, and this will be for the females right here, and this will be for the males, any of these outcomes for females would be considered plausible to us at a 95% confidence level. We wouldn't be shocked by any of those outcomes. So if there's an overlap between all the plausible outcomes where males might vote proportion-wise and how females might vote proportion-wise, if there's an overlap, what do you think that says about the differences between males and females? Yeah. And honestly, we didn't do these two intervals. I don't know if there's an overlap. Let's pretend that there is. So if there is, we would say this is a plausible outcome. This is a plausible outcome for males. And so in this case, females actually voted a higher proportion for this candidate. And what that means is, yeah, there is probably going to be a 0 in the combined proportion. Okay, so let's see if that's true. So now let's come up with this. It's going to be our stat. The confidence interval is the generic formula is a stat plus or minus the critical value times the standard error. If I can write. So your stat here is going to be P hat sub 1 minus P hat sub 2 plus or minus, what's your critical value? It will be 1.96. What do we call that generically? Z star, there it is. But we will plug that 1.96 in a second. Now is a standard error. I'm pulling this straight from the formula sheet. You guys can too. So it's going to be your p hat sub 1 times 1 minus p hat sub 1. I'm not even going to say it out loud. I'll just write it. Okay. What's that? Oh. There it is. So let's do some basic stuff here. What is p hat sub 1 minus p hat sub 2? We're calling that min. Well, we're doing p hat sub 1 minus p hat sub 2. 0.07. That looks good to me. Yeah. Now we did have the critical value. That's 1.96. And now we can plug in these numbers. I will not plug anything in. You guys, and you don't need to worry about writing it on the screen. Just do the math and come up with your confidence intervals. As soon as you've got it, I'll make this very big. We can write out what the confidence interval is right there. All right, so our confidence interval, sorry for that extra delay in there. Our confidence interval went from 0.008 to 0.132. So with this, we can say that it does not include 0, right? So with 95% confidence, we can say that men will vote for this candidate at a higher proportion than females will. And the thing is, now had we done these two before, there would have been an overlap of some small amount, which does give the indication if there was enough overlap, then yeah, this intuitive idea that there's going to be a 0 included would make sense. But it must have been a small amount of overlap, because now whenever we do this calculation where we're combining the variances of both of them, that alters the calculation. And so the question is, which one seems to be the correct approach? Doing two different confidence intervals and see if there's an overlap, or doing the difference of proportions? A 2 proportion Z interval. So does anyone have a thought? Specifically a thought about this question, I guess. Okay. So because I will say this, the 2 proportion Z interval is specifically designed to answer questions like this. Is there a difference in these proportions? And let's create a confidence interval that will show us the likely value of that true difference. So the true difference should fall between 0.008 and 0.132, anywhere from 1% to 13% gap between the male and female vote should be where the true difference is. And this test is specifically designed for answering those types of questions. So this is the better approach than doing 2 different confidence intervals and see if there's an overlap, because those are not really designed to answer those types of questions. Okay. So let's do this. So that was a confidence interval. And now we can do one more t-test. A 9-year study in Sweden compared 21,088 women who had mammograms with 21,195 who did not. Of the women who underwent screening, 63 died of breast cancer compared to 66 deaths among those in the control group. Do these results support the effectiveness of regular mammograms in preventing deaths from breast cancer? So let's look at this. I'm just going to jump straight into the calculations after we come up with our hypotheses. The null is that there is no difference between getting the mammogram and not. So it's going to be the proportion of one minus the proportion of the other equals 0. The alternative, and maybe we need to figure out which one's going to be 1 and 2 here. Are we looking at greater than, less than? So let's, just to make sure it's clear, we'll say that the women who had mammograms will be 1. So this will be N sub 1. That's an N. I don't know why it's not writing there. N sub 1. And this will be the second group who did not get mammograms will be N sub 2.
So it should be greater.
Okay, well, if mammograms are effective in preventing deaths, then the proportion of women who died when they had a mammogram should be less than the.
Oh, I got the 2 mixed up. I thought
Okay.
P1 was in that.
So we would say greater than or less than here. Less than. We would expect those who did not get mammograms are going to die at a higher rate. Therefore, that number should be greater. Let me write it this way. P sub 2 should be greater than P sub 1. And maybe up here at the top, we can write out some of our important numbers. We've got P hat sub 1, N sub 1, P hat sub 2, N sub 2. We are going to need P hat sub 1 minus P hat sub 2. And we need a significance level. And I think we can go with what? For a significance level? 0.05. All right, so 63 who had the screenings died out of 21,088. So you can figure that out. 21,088.
Wait, so the people who didn't have mammograms are the control group?
Yeah, the control group will be those who did not.
Can you pick that, or is that something?
Yeah, how do you know which is like the control group?
Control would mean no change, just if the idea is the mammogram is a treatment that will help decrease the odds of cancer, then that is kind of the change from the norm. So the control would be those who did not. Okay. So the number I got here is 0.00299. And N sub 1 is 21,088. P hat sub 2, let's figure that, that's 66 out of 21,195. So I got 0.00311 with 21,195. And now you can do the difference between those. It's going to be negative 0.00012. Not a big difference, but is it statistically significant? You know what? Dang, we just are running out of time. So I was gonna say I want you guys to do this entire thing. Here's all I'm gonna do. Let's just jump straight down, skip all the other steps, and get down to the test statistic calculation. So just to remind you of that, that's your P hat sub 1 minus P hat sub 2 minus P sub 1 minus P sub 2 all over this fun thing right here. It's going to be your p hat sub c times 1 minus p hat sub c all over n sub 1 plus p hat sub c times 1 minus p hat sub c all over n sub 2. So to get the combined amount, I'm going to take the total deaths, which is going to be 129 out of the combined number of women in this study and not in the studies, or you get it, 21,088 plus 21,195 is 42,283.
This is for p hat sub c, right?
Yeah. 0.00305, which is your p hat sub c. So now go through, we're just going to look at the answer in a few minutes. And if you afterwards are like, you got lost and you didn't come up with the right answer, then we can go through that step by step after the bell rings. Okay, but take this time to solve it. All right, this is indeed, these are the numbers that I got. And I did run through and do the test in the calculator just to make sure, because it can be a little bit overwhelming to do this much calculation. So as far as the calculation in the calculator goes, the test in the calculator goes, and this is a good thing to show you in the last bit, I want you to be in the habit of showing all your work, doing all of this, even doing it by hand. I want you to be in that habit, as annoying as it might be. But in your calculator, if you go to stat and go all the way over to tests and look at option number 6, stat tests option 6 is a 2 proportion z-test. And what you have is X number 1, which is your number of successes for the first group. That was right here, 63 out of 21,088. So the next one down, I know you can't really see my screen that well, but the next one down is my 21,088. And then I had 66 deaths out of 21,195. I had to pick if it was going to be greater than or less than, and then I just go down to calculate. And we're saying P1 is going to be, in this case, less than P2 because the estimate, the thinking is that mammograms help save your life. When you plug that in and do the calculation, it does it automatically. And it gives you a z-score of negative 0.235, very close to what we got, negative 0.236, and a p-value of 0.407, very close to what we got. So this is just confirmation that you did all your steps right. Okay. Again, don't rely on the calculator, all right? So, but it is good to check your work. So with that, I think we've had just a heck of a fun time today. And I hope that this is the ideal way of going right into your weekend. So you have some problems for homework. The progress checks are available. And there we go. On Monday, we're going to jump, it says tomorrow. Monday, we're going to jump into doing some more of this stuff, looking at means and other stuff. All right. With that, if you have any questions, feel free to stick around. If you are good to go, have a wonderful weekend, and I'll see you on Monday.